In our increasingly digital landscape, cybersecurity isn't just a challenge. It feels more like a constant arms race, doesn't it?
It really does. We're always playing catch up.
Exactly, always trying to stay one step ahead. But what if the very foundations of our digital security, the encryption we rely on every day, what if they're facing this existential threat from future quantum computers?
A very real threat.
So today we're doing a deep dive into something pretty revolutionary as a countermeasure: quantum secure communication over free space. And it uses this truly bizarre phenomenon, quantum entanglement.
Right. We're talking about using the fundamental laws of physics, literally, to create communication links that are, well, in principle, unbreakable.
Unbreakable, that's the key word. So for this deep dive, what are we going to unpack?
We're going to look at the core quantum principles behind it, the cutting-edge tech making it happen. We'll highlight some really groundbreaking real-world experiments, from around the globe, including a very significant, very recent one from India. And then sort of look ahead to where this is all going.
Right. And our mission here is really to cut through the complexity. We want to give you the essential nuggets, the key takeaways, so you walk away feeling genuinely informed, maybe with a few aha moments, about what secure communication looks like in the future.
Okay, let's get into it. Sounds incredibly advanced, almost sci-fi. But what's really pushing us towards this quantum approach right now? Why are our current methods suddenly looking so fragile?
Yeah, it's a critical question. See, right now, our standard encryption, things like RSA, ECC, they rely on mathematical puzzles.
Right, like factoring large numbers.
Exactly. Puzzles designed to be so incredibly hard that even our best supercomputers today would take, ages, millennia even, to solve them. Their security comes from being computationally hard.
Okay. Hard for today's computers.
That's the key phrase, because this security is entirely conditional on current computing power. It's not absolute.
And that's where quantum computers stride onto the stage,
Yeah.
right? Precisely. Once we have large-scale, fault-tolerant quantum computers, and that's still a big if on the timeline, but the path is there, they could theoretically solve those computationally hard math problems almost instantly.
Instantly, wow.
Which would just shatter our current encryption standards. Suddenly, almost all our digital communications, financial transactions, secrets, vulnerable.
Okay, that's a pretty stark picture. So QKD, quantum key distribution, is the answer.
It's a leading quantum-resistant answer, yes.
Yeah.
Especially entanglement-based QKD, it offers something fundamentally different: information theoretic security.
Information theoretic security. Okay, that sounds impressive. What's the real difference for someone listening compared to the computational security we have now?
The core difference is huge. Its security isn't based on how hard a math problem is. It's based on the unchangeable laws of physics themselves. Quantum mechanics.
So not math, but physics.
Right. With entanglement-based QKD, you get essentially instant detection of any eavesdropping attempt if someone tries to intercept or even just observe the quantum signals. Yeah. The laws of physics guarantee that this act of observation will disrupt the signal. It leaves a trace. The legitimate users are alerted instantly. It's like a built-in alarm system based on physics.
That's incredible. So it's not just a stronger lock, it's a totally different kind of lock, one that tells you immediately if someone's even trying to pick it.
Exactly. It provides a level of assurance that classical cryptography just can't match.
And you mentioned this also helps with long-range communication, like via satellites. That seems like a massive leap, too.
Absolutely. Because we're using light, we can beam it over long distances, even through space. And perhaps most importantly, looking further ahead, this kind of capability is the very foundation for building a future quantum internet.
A quantum internet. Okay, wow.
Connecting quantum devices securely across the globe.
To really get our heads around this, we need to talk about quantum entanglement itself. It always gets described as, spooky action at a distance.
Einstein's famous phrase. And it is counterintuitive. Basically, imagine two particles, let's say photons, light particles. They're created together in a special way so they become intrinsically linked. They share a single quantum state.
Okay, linked how?
Linked so that no matter how far apart they travel across a room, across a city, even across continents, if you measure a property of one photon, maybe it's polarization.
Yeah.
The other photon instantly, and I mean instantaneously, takes on a correlated property. It's as if they're communicating, but faster than light, which isn't quite right, but that's how it appears. This non-local behavior is absolutely fundamental to how this secure communication works.
It still sounds like magic, even though it's real physics.
It baffled Einstein, so you're in good company. But it's been proven experimentally over and over again. It's real.
Okay, so we have these entangled photons. How do we actually send these incredibly delicate quantum states across, cities or even further? That's where free space optical channels, FSO, come in.
Exactly. Instead of sending them down fiber optic cables, which works but has limitations. What kind of limitations?
Well, fiber optics are great, but over really long distances, they absorb or scatter too much light. The signal loss becomes too high for these single photon quantum states. You just can't get them through reliably over, say, thousands of kilometers.
Gotcha. So FSO avoids that.
FSO sends the photons directly through the atmosphere or even the vacuum of space. We use specialized transmitting and receiving optics, think highly precise telescopes may be mounted on buildings, drones, or even satellites.
So line of sight?
Essentially, yes, point to point. And the beauty is, while the atmosphere causes its own problems we have to solve, FSO channels can span huge distances with satellite help. Over 1,000 kilometers has been demonstrated. This makes truly long-range, secure communication practical.
Okay, conceptually then, how does a system like this actually work without getting totally lost in the weeds? What are the main parts?
Conceptually, you need a few key things. First, an entangled photon source. That's the device, maybe using something called a Sagnac interferometer or an SPDC crystal that actually generates these link pairs of photons reliably. Okay, the photon generator.
Right. Then you need those specialized transmitting and receiving optics, we mentioned the telescopes, basically to aim and collect these incredibly faint signals very precisely.
Precision must be key.
Absolutely critical. Then there's the free space link itself. That's just the open air or space the photons travel through. At the other end, you need incredibly sensitive single photon detectors. We're often talking about detecting individual particles of light.
Wow. Single photon.
Yeah, they have to be extremely sensitive. And finally, you usually have a separate classical channel, like a regular laser link or radio channel running alongside. That's used for things like coordinating, error correction, figuring out which photons got through correctly, that sort of housekeeping.
It sounds like a complex dance of high-tech components.
Hmm.
So what's the core security principle? You mentioned the act of observing causes a disturbance. How does that work with the protocol?
Yeah, the main protocol often used here is called E91, which is based on Bell's theorem. Now, Bell's theorem is quite deep physics, but it essentially gives us a way to test if two particles are truly entangled in that spooky, non-local way.
Okay.
The crucial point for security, for you listening, is this. Any attempt by an eavesdropper, let's call her Eve, to intercept or measure the photons inevitably disturbs their delicate quantum correlations. She can't measure a photon without changing it, fundamentally.
She can't just sneak a peek.
No.
Oh.
It's like trying to measure the exact temperature of a tiny drop of water with a big hot thermometer. The act of measuring changes the very thing you're trying to measure. Eve's interception introduces errors into the pattern of correlations that the legitimate users, Alice and Bob, expect to see.
So Alice and Bob can tell something's wrong just by looking at the results they get.
Exactly. They perform checks based on Bell's theorem. If the correlations are weaker than expected, or if the error rate, what we call the quantum bit error rate, or QBER, climbs above a certain threshold, they know someone's listening in. They just discard that batch of potential key data and start over. Security is maintained because the eavesdropping is immediately detectable.
And you mentioned the no cloning theorem, too.
Right. That's another fundamental principle.
Mm-hmm.
Quantum mechanics says you cannot make a perfect copy of an unknown quantum state. So Eve can't just copy the photon, measure the copy, and send the original on its way untouched. Any attempt to copy introduces errors.
So multiple layers of physics protecting the communication.
That's the beauty of it. Security guaranteed by physics, not just mathematical difficulty.
Okay, the theory is mind-bending, but seeing this actually work in the real world over those kinds of distances, that's where it gets really exciting for me.
Yeah.
Where are we seeing the big successes?
Oh, there have been some major milestones. It's definitely moved out of the lab. One of the early, really significant ground-based ones was back in 2007, the Canary Islands experiment.
Right, I remember hearing about that.
Yeah, they managed to distribute entangled photons between La Palma and Tenerife using telescopes that's 144 kilometers across open water. A huge achievement at the time.
144 kilometers, impressive.
And more recently, there have been urban links, like one between Vienna and St. Pölten in Austria, showing secure communication over about 60 kilometers in a more built-up environment.
Okay, so ground-based links are proven. But satellites, you said, really changed the game.
Oh, absolutely. The really monumental achievement everyone points to is China's MASA satellite, launched back in 2016.
Mecious. Okay, what did it do?
It did several amazing things. It demonstrated entanglement distribution between the satellite and ground stations over 1,200 kilometers.
1,200.
Yes, just astonishing distance. It also successfully performed quantum teleportation, transmitting a quantum state from the ground to the satellite.
Teleportation, like Star Trek.
Well, not quite beaming people up, but teleporting the quantum state of a particle. Still incredible. And maybe most importantly for global reach, Micius enabled the first intercontinental QKD demonstration, linking China and Austria through Italy as well via quantum satellite links.
Wow. So connecting continents, quantum style.
It really paved the way, showing a global quantum network was feasible.
And bring it right up to today, or very nearly, there was this significant breakthrough from India in 2025 from IIT Delhi and DRDO.
That's right, a very important recent result. They successfully set up a secure quantum link over more than a kilometer open air right there on campus.
Okay, a kilometer might not sound like 1,200, but
But the conditions were key. They achieved a secure chi rate around 240 bits per second, which is practical, with a low error rate under 7%. But the really impressive part, they did it in daylight conditions with moving terminals.
okay, why is daylight and moving parts so hard? That sounds like, well, normal conditions for a lot of communication.
It sounds normal, but for quantum signals, it's incredibly challenging. Most early experiments, even Micius for some tasks, worked best at night to avoid stray light, sunlight overwhelming the single photons.
Right, trying to find one specific photon in a flood of sunlight.
Exactly. So operating in daylight requires extremely sophisticated filtering techniques, spectral filters, temporal filters, and highly sensitive detectors that can still pick out the signal from the noise. It's a huge technical hurdle for practical 247 systems.
And the moving terminals part.
That adds another layer of complexity. You need incredibly precise real-time tracking and beam steering systems. Imagine trying to keep a laser pointer perfectly aimed at a tiny moving target a kilometer away. Now imagine doing it with single photons.
Wow. Okay, so overcoming those two things, daylight and movement, is a massive step towards real-world deployment.
A huge step, especially for the intended application here.
Which you mentioned was tactical battlefield communication for the Indian Defense Forces.
That's the stated goal, yes. Developing systems that can provide secure communication reliably in challenging, dynamic, real-world military environments.
That really highlights the strategic side. What kind of tactical advantage does truly unbreakable communication give, say, military or national security operations?
It's profound. Think about secure command and control orders that absolutely cannot be intercepted or spoofed, sharing highly sensitive intelligence without any risk of compromise, controlling drones or other assets with communication links that are immune to jamming or eavesdropping.
Yeah, you can see how that changes things.
In any situation where information security is paramount, having communication you can trust implicitly, guaranteed by physics, that provides a massive advantage in decision-making, operational security, and overall effectiveness.
It sounds like the engineers are really battling the elements, battling physics itself almost, just to get these tiny photons from A to B securely. What are some of the other big technical hurdles they face, sending these delicate quantum states through the atmosphere?
Oh yeah, it's definitely a battle. We touched on daylight noise. Another big one is atmospheric turbulence. You know how stars twinkle?
Yeah.
That's turbulence distorting the light path. It does the same to our quantum signal, making the beam wander, shimmer, lose intensity. It messes up the delicate alignment needed.
So how do they fix the twinkle?
With clever tech called adaptive optics, they use deformable mirrors that change shape hundreds or thousands of times a second, actively correcting for the atmospheric distortion in real time. It's similar to what modern astronomical telescopes use to get clearer images.
Okay, adaptive optics for turbulence. What else?
There's beam divergence. Any light beam naturally spreads out as it travels, like a flashlight beam getting wider.
All right.
Over kilometers, this means the receiving telescope collects only a tiny fraction of the photons.
Less signal.
Right, so they mitigate this using larger aperture optics, bigger telescopes basically to collect more light, and sophisticated active tracking and alignment systems to keep the beam pointed precisely where it needs to go.
We talked about daylight noise, handled by filtering and maybe night ops. What about timing? Synchronization must be critical too.
Absolutely critical. The sender and receiver need to be synchronized down to like nanoseconds or even picoseconds to know when to expect a photon, This is usually achieved using highly accurate GPS-based timing or separate classical laser pulses for time synchronization.
And can the atmosphere mess with the quantum state itself, like the polarization you mentioned?
Yes, that's a big word. Polarization distortion. As the photon travels through the air, its polarization state, the very information it might be carrying, can get scrambled or rotated by atmospheric effects or even imperfections in the optics.
So the message gets corrupted.
Exactly. It increases the error rate, the QBER, potentially compromising security, so they need ways to fix this too. Often they use real-time compensation, maybe sending a bright reference laser alongside the quantum signal. They measure how the reference beam's polarization gets distorted and use that information to actively correct the received quantum photons.
Wow. It's like active noise cancellation, but for quantum light polarization.
That's a good analogy, yeah. It's a constant fight against noise and distortion.
So, okay, stepping back from the amazing tech challenges, what does this all mean more broadly? For you listening, for the world, this isn't just cool physics, right? It has some pretty profound strategic implications and real-world uses.
Absolutely. The applications are significant and growing. We've talked about military and national security tactical comms, secure satellite links for command and control. That's a major driver.
Okay, what else?
Think about critical infrastructure. Securing the communication networks for power grids, for instance, or ensuring the integrity of financial transactions between central banks or major institutions, places where a breach would be catastrophic. Quantum encryption offers a future-proof solution.
Securing the backbone of society, essentially.
Pretty much. And then there's the scientific and industrial side. This technology is essential for building larger quantum networks, which could eventually enable things like distributed quantum computing, linking smaller quantum computers together to tackle bigger problems. And it's the prototype stage for a true quantum internet.
Which could enable things like that quantum teleportation you mentioned, but routinely.
Potentially, yes. Sending quantum states, not just classical bits, across networks. It opens up entirely new possibilities for science and technology.
So it feels like this isn't just a niche upgrade. It's a fundamental shift aiming to protect our most vital systems and information, kicking off a whole new era of digital security.
That's exactly the potential, yes.
Looking ahead then, what's the roadmap? Where is this technology heading in the next, say, 5 to 10 years?
Things are moving quite fast. By, say, 2026, we expect to see more robust 10-kilometer scale daylight free space QKD systems becoming more common, really integrating those adaptive optics and real-time error controls effectively.
Okay, so practical, robust, shorter links soon.
Right. And then looking a bit further, maybe 2027, 2028, India, for example, has stated aims to launch its first dedicated quantum satellite for continental-scale quantum key sharing.
So joining China with satellite capabilities.
Exactly. Competition and collaboration are driving progress. By 2030, there's a general target in the community for a pilot global quantum network, likely involving constellations of quantum satellites linking different continents.
A true network emerges.
A pilot version, yes. And beyond 2030, the research focus is shifting towards even more advanced techniques, things like high-dimensional entanglement.
High-dimensional, what does that mean?
Instead of just encoding information in, say, two polarization states, like horizontal or vertical, you use additional properties of the photon, like its orbital angular momentum, which describes the shape of its wavefront, to encode information in many more states simultaneously.
Okay, and why do that?
Two main reasons. Higher bandwidth, you can potentially send much more key material per photon, and potentially even greater security against certain types of attacks. It makes the quantum state more complex and harder to intercept cleanly.
More information, more security.
Yes.
Sounds like the future direction.
It's definitely a very active area of research for boosting performance.
So let's just reiterate the core message here.
Yeah.
Free space, quantum secure communication using entanglement. It's not just theory in physics journals anymore.
Not at all.
It's being built, tested, deployed in the real world. We've seen huge successes from China's MISIS long-range ground links in Europe, and now India showing really significant progress with its capabilities, especially for practical deployment. It's happening now.
It really feels like the dawn of a global quantum internet infrastructure. It promises that unbreakable encryption we talked about, offers significant tactical advantages, and it's really ushering in a new era for how we secure our digital world.
Absolutely. And as we wrap up this deep dive, here's something for you, the listener, to think about. If our critical infrastructure, our military comms, can achieve this level of essentially unbreakable security thanks to quantum entanglement, What might a world truly secured by this technology mean for your personal data, for your privacy, your everyday online interactions down the road?
Yeah, how could this shift the balance of power between individuals, corporations, governments?
Or could it even enable entirely new forms of digital life and interaction that we can barely even imagine today once that foundation of quantum security is in place?
Yeah.
Something to mull over.